Module Overview. This module dives deeply into the science and psychology of color perception, the role of light in how colors are experienced, and how optical illusions and context can drastically alter our interpretation of color. Unlike the physical properties of pigments and digital color systems, this module focuses on the human visual system, how it processes color, how environmental and emotional factors influence perception, and how designers and artists can intentionally manipulate visual perception to achieve specific effects. Understanding color perception goes beyond mixing hues. It is about grasping how light physics, human biology, cognitive biases, and contextual variables interact to shape what we see and feel. 1. The science of color perception. 1. The human visual system. The human eye perceives color through cone cells located in the retina. There are three types of cones: S cones, short wavelength, blue; M cones, medium wavelength, green; and L cones, long wavelength, red. The brain processes signals from these cones to create the experience of trichromatic vision. Rods are responsible for night vision and do not detect color. Color perception is a product of both the eyes and the brain. 2. Color and light. Light is a form of electromagnetic radiation. The visible spectrum is a narrow band of wavelengths from roughly 380 nanometers, violet, to 700 nanometers, red. White light, like sunlight, contains all visible wavelengths. The color of an object is determined by the wavelengths of light it reflects and absorbs. For example, a red apple reflects red wavelengths and absorbs others. 3. Additive versus subtractive color. Mixing. Additive, RGB. Red, green, and blue light combine to form white. This is used in screens and digital displays. Subtractive, CMY/CMYK. Cyan, magenta, and yellow pigments subtract wavelengths to create black or dark tones, used in printing and painting. This duality shows how color behaves differently depending on the medium and light source. 2. Factors that influence color perception. 1. Simultaneous contrast. The same color appears differently depending on adjacent colors. Example: gray on a red background looks greenish. On blue, it may look warm. Artists like Joseph Albers studied and demonstrated this effect in color theory practice. 2. Color. Constancy. The brain adjusts our perception so that the colors of objects remain constant under different lighting conditions. For example, a white shirt looks white under blue light, even though it's technically reflecting bluish tones. 3. Lighting temperature. Light sources differ in color temperature, measured in kelvins, K. Candlelight, 1800 Kelvin, warm yellow-orange. Noon. Sunlight, 5500 Kelvin, neutral white. Overcast sky, 6500 Kelvin, plus cool blue. This affects how colors appear. A warm painting may look dull under cool lighting. 4. Surrounding environment. Colors are influenced by nearby hues and ambient surroundings. Painters and designers must test palettes in actual environments before finalizing. 3. Optical illusions and perceptual phenomena. 1. Afterimage effects. Staring at a color for a long time, then looking at a blank surface can cause an afterimage in its complementary color. This is due to cone cell fatigue. 2. The Bezold effect. A color's appearance can change dramatically when placed next to a different hue, especially in pattern-based design. 3. The Munker-White illusion. Identical colors appear different because of surrounding patterns or color bands. 4. The Dress 2015 phenomenon. A viral optical illusion where people disagreed if a dress was blue, black, or white, gold, explained by individual assumptions about lighting and shadow context. 4. Applications in art, design, and psychology. In fine art, Impressionists manipulated natural light and atmospheric effects. Op art, optical art, artists like Bridget Riley used illusion to create vibrating movement. In design, designers use color manipulation to draw attention, create depth, or create brand emotion. Example: web call to action buttons that pop due to complementary contrast. In psychology and marketing, understanding perception allows companies to influence mood and behavior. Warm colors trigger urgency, used in sales. Cool colors are calming, used in healthcare. In safety and accessibility, color contrast is critical for visual accessibility. Understanding color blindness, e.g., red-green, ensures inclusivity in design. Conclusion: Color perception is not fixed, it is fluid, context dependent, and deeply tied to human biology, psychology, and environment. A color only becomes meaningful when seen in relation to light, context, and the observer's brain. Mastering this module allows designers and artists to predict how viewers will respond to color, avoid unintended visual confusion, build emotionally powerful and perceptually balanced compositions. This is not just science, it is visual psychology in action.